Hello, welcome Railways Africa readers. We're here at ZUTARI for a coffee with the editor, and we're going to be talking about decarbonising tractive effort. Thank you for joining me. We're talking about decarbonisation of tractive effort, and I think really it's the possibility of what the future could look like. And obviously I'm quite excited about what that future looks like from a South Africa and Africa perspective. But the presentation that you guys gave a couple of weeks ago at the University of Pretoria really was fascinating. And which one of you is going to give a little overview of what that was?
So what we spoke about at the University of Pretoria is essentially how we can utilize battery electric locomotives, specifically in a heavy haul rail space, to facilitate decarbonisation. And it's a very interesting field because a lot of the technology is already there, the technology readiness. We're at the point of system integration, essentially, and operational trials and testing how all these systems come together. Why specifically in the heavy haul space is because, in general, when we talk about heavy haul rail, we are taking bulk materials from a mine, generally somewhere above sea level, down to ports at sea level, and the train's loaded from the mine to the port, and then it goes back empty. And there's a lovely thing that happens with the energy balance there, because we are essentially breaking the train almost all the way down the hill, and then we're taking this empty load back up again. And so you have a lot of gravitational potential energy, and to break the train on the way down the hill, you can actually harvest that energy in a form of regenerative braking.
That regenerative braking, is that not something we could have actually put back into the grid?
Correct.
In our own operations here? Why aren't we?
Jan can chip in here if he wants to. You probably know a bit more about the ore line and the coal line and how that was designed, because I think that is part of the design.
So in South Africa, we have two feeder systems to the train network. The one is direct current, or DC, feeder stations, and the other through AC feeder stations. And on the DC side, you cannot push it back into the network. But on the AC side, like our heavy haul lines, there you can push it back, and they do that already, but to the point where that energy is available on the overhead, and a train that's also in the vicinity can use that regenerative energy.
Is that happening?
It is happening. It doesn't go into like a communities using the next doors, and so it's just for other trains. It could essentially, but there are limitations to that. So the line lengths, there's lots of losses if it needs to be transmitted for long lengths. So it's not effective. The efficiency of that is low.
Yeah. So basically, what's happening now is it's being discharged, and it's not really being taken up anywhere else. And if I understood from the presentation, and maybe you want to pick up here, is that with the batteries on board, you can actually put that power back into the batteries, which would get you back up the hill on the way home, empty.
Yeah, and I think in the current situation, you have a lot of rail networks that's not already electrified, so it's great that you can push back that energy on existing systems. But if you do not have any overhead wiring that you can use to push that energy back in, can you not store it on board? Can you not store it locally? If you look at the electric vehicle market, you have your Teslas. If you go down here, it brakes, it pushes that energy back into the battery. So that technology already exists. It works. We know it works well, and it's pretty high efficiency that you can capture that energy back into a battery. So it stands to reason why not utilize that for railways, given that you have this massive amount of mass that you're moving from a high point down to a low point, similar to a hydro dam, same concept.
And does that altitudinal difference also make a difference?
Yes, the elevation profile of the specific line on which you would want to implement battery electric locomotives is very important. In an ideal case, if you just have a straight line between your mine and your port, perfect. Then you don't have to ever take your loaded train up a hill, and you've basically got free energy the whole way down that you can use to get back up. It doesn't work like that in reality, and your elevation profile would make a difference as to how much regenerative energy you can actually capture, and how much tractive energy you need as well to actually get to your port. Because you might sit with the situation, let's say your mine is at 100 meters above sea level and your port is at 0, but you have a 500 meter high mountain in between that you need to get over. That's less than ideal, because you need to now use a lot of tractive energy to get up the hill first before you break the train going down the other side. So that topology is not...
And you'll have the same problem going even though you'll be empty, you'll have the same problem going back.
So the topography makes a huge difference, and that's where it becomes a very interesting optimization problem about how big must the batteries be, or how many of these bells do you need within a train, or where are you going to include some en route charging infrastructure, possibly would it be static charging, on the fly charging?
Let's just talk about that tractive effort, because the one thing about a diesel locomotive is, like, they're heavy, they're strong, they're 4,000 horsepower coming out of that engine, but that's not where the secret is. The secret is in the traction motors. So talk to me how that is then impacted by the batteries.
Power for motion is given by the electric motors that sits on the axles. Now these electric motors can already regen to help braking the locomotive, and it does it. But currently on the diesel electric locomotives, that energy goes into resistor banks and is just wasted. So moving then from a diesel electric to something like a battery electric is changing that source of power from the diesel engine to a battery pack, big battery pack, but then still keeping the same or equivalent electric motors that has the same power output than in the diesel electric locomotive case. So then you still have the capability of having regenerative braking, but now you push that energy into the battery pack for storage until you need it.
Would we have to kind of look at how to advance traction motors, or the traction motors okay as they are now?
I think they are advanced quite enough for the power that we need for trains, and they do change as we go for longer or trains, and I think that is. I don't think we need to change anything there, going from diesel electric to battery electric.
In your view, how practical is it for South Africa and certainly Africa to do this leap? And I call it a leap because we have issues with electricity, and we have issues with diesel locomotives. Never mind just the decarbonisation, but like the cost of them. And also, one other question: could we take our existing rolling stock and re-engineer to retrofit with like a diesel? I mean, the battery dual power thing.
Yeah, I think it's very applicable for us as a South African or African context, given that we do have quite significant issues when it comes to vandalism, theft of overhead wiring, that you cannot run a train even if a short section of overhead wiring is now no longer functional for that train to run. So as a stopgap solution, a battery train allows you to run certain sections where there is overhead wiring and then certain sections where there is not, because you are carrying that power on board. So as a leap, I think it definitely indirectly addresses a lot of those challenges that we currently face. That's maybe not necessarily a primary cause of concern in the outback, where there is currently no electrification at all. So there's also an infrastructure cost aspect if you have to electrify the entire rail network, versus can you not rather use more expensive battery electric locomotives that are more expensive, say, than diesel ones, but it's that cost implication of retrofitting an entire network in Australia versus the African context. We do have infrastructure, but perhaps not suited entirely for us to really maximize the throughput that we would ideally want on our railway network.
There are a number of OEMs who are already looking at this hybrid, I'm going to call it hybrid technology, because I think that's what it is. What is the investment? Because I think we also said that this was quite expensive. There's going to be a significantly increased investment threshold versus a new diesel locomotive.
Definitely. Battery electric locomotives will cost more than an equivalent diesel electric locomotive, and that increased cost is primarily due to the batteries and the battery management system. That's the expensive, the part that adds to the cost. You are getting rid of your diesel engine. You no longer have a diesel engine, but batteries way more expensive. You can compare it to if you want to buy an electric vehicle versus a normal internal combustion engine vehicle. The prices are completely...
Yeah. And then the maintenance on that, and the longevity of life cycle longevity. I mean, is this a winner or not?
The jury's probably still out on that, because I don't think, or definitely not battery electric locos, haven't been around long enough to really answer that question with confidence. But I think the battery technology has been around long enough to say that the current battery chemistries that we have do last. There have been papers published that have actually shown for EVs that some of our estimates are actually quite pessimistic, and that the batteries last quite a bit longer. So that's positive and encouraging. How that translates to battery electric locomotives, the jury's still out on that. Yeah. You mentioned maintenance. A diesel loco is probably a lot more maintenance heavy than a battery electric loco would be. There's a lot more mechanical parts, a lot more moving parts. With a battery electric loco, you're basically just working with electronics. So maintenance costs, if you now just normal, I want to say routine maintenance, is probably going to be quite significantly lower. However, when it comes to battery replacements, that's going to be your big cost.
And also, I think in the battery technology, that's also still being developed, and we are going to get higher energy density and with more life cycles that you can put them through, and so the longevity of the batteries are going to increase. So it's good that we start on this now, so that when and see what is the capability of a system like this now, and that will, I believe, get better as battery technology improves.
I think it links well to the decarbonisation topic as well. If you have enough life of your batteries on board a train and they can only store a reduced amount of capacity, you always have the possibility of having a second life for those batteries as well, potentially for battery electric storage on your renewable grid that you now need to power and feed these trains with electricity ultimately. So that forms part of the bigger life cycle of the asset that you're managing, and potentially a second use case for that component that you might not have with a diesel loco once it's retired.
Yeah. So I think in the passenger space, I think the battery electric is a little more advanced, certainly in developments and user case over the freight side. So the scenarios in the outback where you were playing are different to what we have here in terms of how the asset, the infrastructure and everything is owned and used from an efficiency perspective. I was blown away actually by the numbers that I read. How do we and it's it was like under 500 kilometers. How do we then, using that technology, using the theory and practice and what do you call it, computational
design. It's very much still that R&D space that we're working in, because there's no design set standards on how you're actually going to deploy and develop this technology. It's still brand new.
Okay. So taking all of that and then applying it to our South Africa's heavy haul market, where the lines are obviously much longer. There's only one. I don't actually know how many available locomotives are running on it, or wagons, but how would it work? Could it really be practical in the long term?
My colleagues here, that's where they shine, and that's where they do the magic on the computational methods. To maybe put that in perspective, we do have different corridors in South Africa. So, for instance, the Oryx line is more or less 800 kilometers, but it will be a dedicated corridor. So we will have to look at that apart from the rest of the network, if we would consider something like that. And the same with, let's say, the Natal corridor or the coal corridor. And then there are various, so we won't look at it as an entire network, because there's different rolling stock and different commodities and different trains running on different corridors. So I think first we will separate those.
Heavy haul, so I want to apply it to the same concept as what you've been doing in the outback.
Then we're playing with two lines, essentially. It's the ore line and the coal line. Those are our heavy haul lines in South Africa.
But the computational methods that Rick and André has been developing can definitely be used on these corridors and with the different trains and commodities and the different infrastructure.
Solution space, so we can really modify and run different permutations of where can we charge the trains. Is it going to be on route charging, so what we also call sometimes mid-journey electrification, so charging them while they are moving. Where do you place this infrastructure? How long should it be? And that's sort of the techniques that we've developed in optimizing that solution to check, will it work, how will it work, and are we taking into account events where the environment might impact that, or you're using a lot of energy for some reason for a certain trip. Make sure those trains will not run flat.
An idea of an average speed here?
Typically for heavier operations, Rick, you've had a look at speeds, but it's not high-speed passenger rail, so that benefits us in terms of aerodynamic performance, I would say.
What we have noticed with a lot of the modeling we've done is that if you travel a little bit slower, it will help those batteries oh so much. It's not about getting to your destination very fast and then sitting and waiting for an available slot to open to offload or load. You rather travel a little bit slower. There's a lot less wind resistance, and that means that you save a lot of energy. To come back to how we can use this in the heavy haul line, on the heavy haul lines in South Africa, some of the computational design tools that we've put together, essentially if we have your train consist, your configuration, how many locomotives, wagons, what are the weights of those wagons, the elevation profile, you put that into the tool, and then you have a bunch of knobs and dials that you can tweak. So then you say, okay, where do we want, you'll simulate your battery state of charge based on a speed profile and a number of stops en route, and then likely it's a long route, you're not going to make it with current battery sizes on the locomotives, so what you want to do is put some kind of en route charging in place. Then you can start assessing, okay, where would it be most ideal? Immediately, you would prefer to put en route charging over steep inclines, because your trains are naturally moving a little bit slower in those areas while they're climbing those hills. And while you're climbing those hills, you charge the battery, but you can also replace the tractive effort that those locomotives need to get up the hill. So you get double bang for your buck if you put your OLE over those areas. If you can't, for whatever reason, if it's in an environmentally sensitive area and you can't put let's say the substation infrastructure next to your track, then you'd consider alternative areas. You can also, another dial that you can tweak is how much power can you feed in from your OLE. You can increase that, decrease that. That'll change the length of the overhead line that you need to charge up to a specific point. So there's a bunch of dials that can be tweaked to see what works. That's just a starting point. It's nice to sit with the client, with the tool open, and actually discuss it with them in person and change those parameters with the client, watching the results.
You were talking about how many data set points coming in at any point?
It can be up to a few billion points that we are considering, because we can have simulated data for these trains, we can run models on computers, we can get existing information and data, say, from site. And these are high resolution types of data points. In terms of every number of seconds we get a data record. There's lots of trains, they run for a long time, so it is really a big data application for us.
And it's live data that's coming in?
To some extent, all very recent data that we've perhaps collected during the last year or so, but that presents to you a complete picture of what's happening on the ground. And then you always look for those events that sits on your ends of the distributions to make sure that all trips are catered for, not just a single trip. Because even in the Pilbara area, they have the issue, for example, with cyclones that's periodic in that area. So perhaps it's not about just the speed of the train necessarily, but if there's a wind of 100 plus k's an hour blowing against your train, you're going to use a lot more tractive effort to get that train from point A to B. So is that accounted for in your data?
In those kind of weather conditions, would the train still run?
Unlikely, not 100 kilometers per hour winds. That's probably all operations will stop.
But they will operate, let's say, at 70 or 80 kilometers an hour, headwind or tailwind. So, and that over a period of time can be significant from an energy point of view.
And those conditions will change depending on where those operations occur. If it's not in a cyclone area, then you're unlikely to have wind speeds like that. You wouldn't have to account for it to the degree that you would have to in a cyclone area. So you might not have to design your train to be able to operate in a constant headwind of 80 kilometers per hour. It's going to be very specific to the area where the battery electric locos are implemented.
So let's talk about how a current consist works. So you have, and you can correct me because I think it's been a while since I remembered this. You've got two in the front, then you've got a whole lot of wagons, and you've got another one, we call it distributed power.
Yep,
how all of this comes together. With the battery electric locomotive, would you need more locomotives?
It depends, is the answer. What it depends on is a number of things. One being, okay, so for example now, axle load is important. If you can run, batteries are very, very heavy. So if you put batteries onto your locomotive now and you have a battery electric locomotive, if you can increase your axle load more than what the diesel loco was without exceeding the track limits, you might be able to actually exert more tractive effort through that battery electric loco, just because you've got the mass. What's important is the more mass you have on the rail, the more you... Yes. Given the same traction motors now, assume that your traction motors can provide more traction than what can actually be transferred between the wheel and the rail, because it's going to slip eventually. If you increase the weight, you can transfer more of that power. So that's one aspect.
If you're saying if it's going to be a sufficient number of locos, and that's where it links up with Rick's, it depends. Yes, you can add more. The benefit of that is we're confined currently how much energy you can have on a single locomotive. So instead of 4, what if you... To some extent, weight, mass, physically how many batteries you can put in there. But let's say you wanted to... Volumetric constraints, if you had to put a name on that. So let's say instead of 4, you had 8 locomotives, then you had double the battery capacity on board. But these things are expensive. So how does that feed into your financial cost model if you need to replace these batteries in a certain number of years? So there is a bit of a trade-off. More batteries, then you need less infrastructure. But again, where's that capital and operating expenditure going to go ultimately? And we're running various scenarios and permutations on that to say it might even impact your operations if you now have more or fewer locomotives in that consist. Maintenance, if they need to maintain more locos, that could also have an impact. So it's a very wide-reaching impact of, yes, we're looking at energy or tractive effort, but it spans across the entire asset portfolio or network for an operator.
So, hence why I was asking about the retrofitting. Like, could I take an old Class 34, which is a diesel, rip out all the insides and remake it in very simplistic terms, guys, very simplistic terms, into a hybrid diesel electric locomotive. That way I would have reused an asset that's actually in perfectly good condition, that is in line with the weights of an axle load of my current track, and I didn't have to go buy a new one. Is that possible?
Yes, and if you then still have the same electric motors on it, there might be a 1-to-1 replacement from a diesel electric to this battery electric. What then will what the operation will depend on is what the amount of batteries or the volume of batteries that you could get into the space that was now available on inside that locomotive is whether you can now complete a full journey with only that battery pack, and see where do you need to recharge and where can you recharge, and that's where these tools that they've developed, it comes in handy to tell you if that is possible. But from a rolling stock point of view, there can be a 1-to-1 replacement.
How heavy is this battery electric system versus a diesel engine? Because there is a weight issue. That's the first one. And then the second one is, could I have a power coach as part of my consist to solve the problem?
Like a coach that only carries a battery coach.
Well, like a power coach. Yeah. What would you call that?
Are you referring to EMUs, like car train, where the engine, the traction motors are built into the coach?
Yes. Well, there's...
So you have like that on the wagons, essentially.
Locomotive without a cab.
Dedicated...
Just for additional battery energy storage. I like to refer to that sometimes as the fender trailer approach, that you just sort of drag along additional batteries.
You know, just in case, like in the middle. Do you have a fancier term?
A battery electric tender. So that's essentially a battery pack. It's your fender trailer behind the battery electric loco, or it doesn't even have to be a battery electric loco. It can be a diesel loco, which has been retrofitted to operate with the battery pack, the battery electric tender, on the next wagon.
They can also regen and add more regen.
So it self-powers almost.
It could be, in a true sense, a true hybrid, because then you have still your diesel engine on that loco, plus the battery pack.
Okay, what were you saying? The wheels turn and the traction motors are underneath at the battery?
So you gain even more regenerative braking if your tender car can also has motors on it that can help brake and store more energy.
All right, so I think that's a great idea. I think that would work for our 800-kilometer or above lines.
Indeed. The more traction motors you have on your train, the more dynamic braking energy you can essentially generate and then store. Yeah. You can't brake the train more than it needs to be braked.
Would you have to change the braking system that's on the train to accommodate this?
There are certain in-train forces, so the philosophy of and how fast you can do this, that needs to be planned and checked for different braking schedules, but that can be done. But from the installed braking systems, you don't need to change anything.
There is perhaps also room for optimization. So if you look at, it's still human operators for the most part, so it's not computer systems that can aid us to more effectively manage the energy in that system that we can get back into the batteries, or then physical limits on the performance of a battery electric locomotive. How much energy can you actually store in the batteries? Do you have excess energy that needs still to be dissipated as heat? Or then back to, if we add more battery electric locos, we might be able to store all of that energy. So that's the optimization side of things, where we can still gain perhaps a few more percentile points in terms of energy. But this is a huge quantity of energy, so every bit that we can capture back is beneficial.
So, and then all you do is you take all of this information, you put this in this very fancy tool, and then it spits out different scenarios.
Yeah, so for us, tuning the knobs and dials, it's also in terms of practicality, but for us, it's the human element that you don't want to lose in that. I like to always talk about human-in-the-loop automation. It's great to sit with a client and discuss with them. These are some of the options or considerations that we have within the constraints that we typically operate. But then questions might come, how practical is it to build this section of electrification in the middle of the desert? Or it's maybe perhaps more logical to divide it up into two sections. Or in terms of a risk scenario, what would that look like if a train can run flat? Is it not better to position it closer to the port, closer to the mine? So that real-time engagement for us is really where the value addition for us lies, to do this real-time engineering or optioneering exercises that we can do. Take their feedback, we can implement new features and functionality that we are doing over the course of time. And that to us gives us, I think, a much more robust solution set. And it's an ongoing involvement and evolving solution that we are looking at, even as circumstances might change. So it's a very dynamic system, and that's really what makes it an enjoyable project to work on.
By no means is it a software tool like Microsoft Word, where you're fixed to this is what you can do with it, and you're going to have to wait a couple of years for the next update. This is we're not software engineers. We're engineers that enjoy coding essentially, and so it's very dynamic. And as the needs arise, we implement those. We change the tool to address those needs.
There's lots of efficiencies that come from it, both in the data handling part, but also in engaging with the client. And that is what I saw when we engage with the client on the tool, because you can change. It's very visual, and you change a small thing, and they see on the map where it is, and the client will say, "Oh no, we have that infrastructure there. You can't do it there," and you change it immediately. So you get this feedback very instantly from the client, and that engagement is helping the development really go at a good pace.
So if you want to hear more, the team will be at the Heavy Haul Conference in Colorado. I want you to close on where you think the future looks. Is it the battery electric? Is it the hydrogen? Is it something else?
This is obviously my opinion, and I would be happy to be proven wrong at any stage. I believe that battery electric locomotives will become a normal part of heavy haul operations in the near future. I think it's going to fill the gap essentially between our current modes of propulsion and once hydrogen is at a readiness level that it will take over. I think it fits that gap nicely, because something about hydrogen that I think people often don't realize is that, except for hydrogen internal combustion engines, which I don't think are extremely popular and at a readiness level to be used just yet, hydrogen fuel cells also have batteries. That's how they work. So I think a battery electric locomotive is a nice, it'll fill that gap until hydrogen is at the readiness that we can, it'll take over. How many years that is, I have absolutely no idea.
And you're not still looking at, like, the traditional diesel engine and maybe the change in the kind of diesel, so a more sustainable diesel or a biofuel version?
It's a good question. I don't play around in the biodiesel space a lot, but my understanding is that it's extremely expensive. even more so than implementing solutions like battery electric locomotives.
Decarbonisation in the railway space?
I'm excited about battery electric locomotives, and I think, especially in Africa, which has different challenges than other parts of the world. There's a place and application for it that's a little bit different. And there's lots that we can still develop and needs to be developed in terms of operations and interfacing to other rail systems if we do implement battery electric locomotives, whether it's a brownfields, an upgraded line, or whether it's greenfields. I think there's still plenty to do. So I'm excited about that.
André, your thoughts?
To put it some numbers in global context as well, about 40% of the world's iron ore production comes from the Pilbara region alone. I think it's close to 1 billion tons per annum that comes from that region. So the world runs on steel and to diesel to a large extent, but I think the technology readiness level for battery or hydrogen is there to be a substitute for existing diesel. Most of the areas that we do heavy mining typically is associated with sunshine, so you can get your renewable energy right at the source where you want to use them with the trains. So that indirect impact of decarbonising not only the heavy oil space is also going to have quite a big impact on the worldwide consumption of those commodities that we ultimately produce. And I think that's a double impact from my side that I'm excited about to contribute our work to the world.